Today we're going to talk about momentum and impulse. Momentum is a quantity of motion and is found by multiplying mass times velocity. The symbol for momentum is a p, and so the formula p is equal to m times v. Momentum equals mass times velocity. Impulse is defined as the change of momentum. And the change of momentum can be calculated as well. Symbol for impulse is a j. J is the impulse, and that equals the change in momentum, delta p. Remember, delta means final minus initial, so p final minus p initial, or in other words, mass times v final minus mass times v initial. That's how you find the impulse. Impulse can also be found by taking the net force and multiplying it by the time over which that force is acting. So we have a formula then for impulse. We can look at it this way. J equals delta P equals m delta V equals F times T. And F times T also implies that you can take the area under a force versus time graph to find the impulse, which again, impulse is the change in momentum. Good equation to know here, good equation to know here. We also know that momentum is conserved, so we have conservation of momentum. And that is implied in this formula right here, that the net force multiplied by the time is equal to the change of momentum. So if we have a system of objects and there is no external net force, if the net force is zero, the outside net force is zero, then the change in momentum must be zero, which implies that momentum must be conserved. So conservation momentum applies whenever there is no outside net force and momentum conservation basically means that the initial momentum of a system is equal to the final momentum of a system, or P initial equals P final. Now, if we have a two-object system, we often will just write this as m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. So here I'm using this little prime notation to denote final to distinguish it from initial. We've got plenty of subscripts here. We don't need to throw in a bunch of extra subscripts. But that's your basic equation for conservation of momentum. There are different applications of conservation momentum, and let's look at a couple of examples. Let's suppose we're looking at a situation where we have a 2 kilogram block and a 3 kilogram block on a frictionless surface. The 2 kilogram block, initially moving to the right at 3 meters per second, is going to strike the 3 kilogram block, which is initially at rest. As a result, the 2 kilogram block will stop completely, and the question is, what is the final velocity of the 3 kilogram block? It's helpful in conservation of momentum problems to draw a before and after diagram, similar to what I've got here. So this would be my before diagram. This would be my after diagram. So there's a collision, some kind of interaction that's happening. So in the before diagram, I've got this, and my after diagram, I've got it like this. So the way to set up a conservation momentum equation is that your momentum initial of the system is going to equal your momentum final. One way to look at that is to simply take mv for each object initially, add them together, that's your initial momentum. Take mv for each object afterwards, that's your final momentum, and you set them equal. So here I've got 2 kilograms times 3 meters per second plus 3 kilograms times 0 meters per second at rest equals 2 kilograms times 0 meters per second plus 3 kilograms times an unknown velocity. So as I simplify this, I see that I have 6 on the left equal to 3v, and I simply solve this and I get 2 meters per second is my velocity of this object. Now notice that I chose a positive velocity for to the right here, and as the answer came out positive, I know that this block is moving at 2 meters per second to the right. That is the final velocity of this block. And that's pretty much how you solve a conservation momentum problem. Let's look at another example. Here we're going to do an example of what we call this a sticky collision, where I've got one object that's moving and it's going to collide and stick with another object. In this case, I've got some train cars. I've got a 12,000 kilogram train car moving at 2.5 meters per second to the right. It is going to collide and stick to an empty train car that's 3,000 kilograms. That is initially at rest. So the first thing I want to do in a conservation of momentum problem is to sketch my before and after diagram. So I've already got the before diagram here. A little squiggly line here, and then my after, they're stuck together. So their combined mass, I'm going to go ahead and combine those numbers. So now I've got one object that has a mass of 15,000 kilograms, and I don't know how fast it's moving. This is my after. So my before diagram, my after diagram, again, P initial equals P final. That means I do MV for everything over here equals MV for everything over here. So here I've got 12,000 times 2.5 meters per second plus 3,000 times 0 equals, over here I've got one object, so I just do 15,000 times V. So 12,000 times 2.5, that's 30,000, plus 0 equals 15,000 times V, and then I can solve this for V by dividing by 15,000, and I get 2 meters per second equals V. Again, to the right was positive, and therefore the answer coming out positive means after the collision they will move to the right at 2 meters per second. That's an example of a sticky collision. Let's do another example, a head-on collision. So in this case, I've got a 10,000 kilogram truck moving to the right at 15 meters per second. I've got a 2,000 kilogram car moving to the left at 30 meters per second. And let's suppose that they collide and they stick together. And I want to know what happens after the collision. So again, this is conservation of momentum. So I'm going to draw my before, which I've already got. Do my after. So after, they're stuck together. They're combined, so their mass now is 12,000 kilograms. And I don't know how fast they're moving. So let's take a look at this. P initial equals P final. That just means MV of everything over here equals the MV of everything over here. So what I've got over here on the left, the before, I've got 10,000 times 15 plus 2,000. Now the velocity here, if 15 to the right, if 15 is positive, then 30 to the left has to be negative. For conservation momentum problems, I have to pay attention to the direction. It matters. So if I've got positive is to the right, then that means that left has to be negative. So this becomes negative 30 equals my combined mass over here, 12,000 times V. So this becomes then 150,000 minus 60,000 equals 12,000 V. So that's 90,000 equals 12,000 V. I simply divide 90,000 divided by 12,000, and I get 7.5. Notice that my answer is positive. That means that after they stick together, they're still moving to the right at 7.5 meters per second. Notice what that means in practical terms. If you're in the truck, after this head-on collision, you go from 15 to the right to 7.5 to the right. Okay, so you slow down a little bit. But if you're in the car, the little car that's going 30 meters per second to the left, now you're suddenly going 7.5 meters per second to the right. You've experienced a much larger acceleration as a result of your much smaller mass. So those effects are certainly felt differently. What are the units of momentum? Probably should have talked about this earlier. But if we look at the formula, P equals mv, the units of momentum will be the units of m, units of mass are kilograms, times the units of v, units of velocity are meters per second. So the units of momentum are kilogram meters per second. Now we also know that impulse equals the change in momentum equals mass times change in velocity equals force times time. So change in momentum is going to be kilogram meters per second minus kilogram meters per second. So we have just kilogram meters per second there. But we can see here force times time, that's newtons times seconds. So kilogram meter per second is the same thing as a Newton second. So either one of those will work just fine as the units for momentum.